All right, guys, we're here to talk about the mean value theorem today and how we can apply that to a graph that is a function. So, what the mean value theorem says, I'm going to read the definition, but then once you see it, the definition will make a lot more sense. So, f has to be continuous on a closed interval from a to b and differentiable on the open interval from a to b. It says then there exists a number c, so some c in that interval a to b, where the instantaneous rate of change equals the average rate of change. Okay, so basically they're saying the slope, the average rate of change, so the slope from the endpoints, is equal to the derivative at some point in between there. Okay, so let's take a look at this first part here. So in the little bubbles here, little clouds, so f prime of c, okay, here's f prime of c. That is the instantaneous rate of change. So we'll start off with that. Instantaneous, forgot my s there, rate of change. Rate of change. And we're saying at x equals c. So we don't know what that value of c is, but you know, it could be 1, it could be 2, it could be a decimal value, no problem, right? On the right side, you see what looks like our slope formula over here, f of b minus f of a all over b minus a. This is the average rate of change. Average rate of change. And this is on the interval from A to B. All right, so let's kind of see how this works. Down below here in example number 1, it says the graph of negative x squared plus 4x, that's that partial parabola on the interval from 0 to 3. So that's what we've got over here is the interval 0 to 3, a partial parabola. And it says draw a secant line through the 2 points at the ends of the interval. So I'm going to start off with that. I'm going to draw or attempt to draw a secant line here. So let's see what I can do here. All right, so there's my secant line. And it says to find the slope of that secant line. Now, I can find that slope by doing f of 3 minus f of 0. Those are the two y values at the endpoints, all over 3 minus 0. And if you look on the graph here, okay, I'm just going to take it off the graph today. We've got the point 3 comma 3, so that's f of 3 is equal to 3. F of 0 is down here, that's equal to 0, and that's all over 3 minus 0, and you can see that we're going to get a slope of 1. And we could have counted that as well. If you just count the rise and the run, you'll see that the slope is 1. So I know that the slope through there is 1, and part B says draw a secant line, or excuse me, draw a line tangent to the graph that is also parallel to the secant line. From the graph, approximate the coordinates of the point of tangency. So what I'm attempting to do now is I'm going to come over to my graph here, and I'm going to put a point on the graph here. Actually, I'm going to take my ruler, and what I'm going to do is I'm going to attempt to draw a line that's parallel to that first one. See how well this works out here, okay? And, nope, not quite there yet. There we go. Hey, not too bad. That looks pretty parallel, doesn't it? And so I made that line a tangent line, and you can see that somewhere right about here is where that point of tangency would be. So I'm going to approximate that as maybe x equals 1.5. So we'll say 1.5, and the y value there looks like it's, I don't know, maybe 3.75. Okay, anything you want to do there is close enough. Okay, so I've got two lines on my graph. They're supposedly parallel to each other. Okay, and then part C says, okay, now we're going to calculate f prime of x. Okay, so that's the next thing I'm going to do. I'm going to calculate my derivative f prime of x. That's going to be equal to, and I'm going back to the original function f of x here. That's negative 2x plus 4. All right, and part D says set f prime of x equal to the slope of the secant line and solve the equation. So let's go back up here for a minute. Remember these little clouds up here? The instantaneous rate of change, that's f prime of c, okay, and we just calculated that, is equal to the average rate of change on the interval. That's what the mean value theorem says. And that's what we're doing here in part D. We are taking f prime of x, so that's negative 2x plus 4, and we're setting that equal to the slope of the secant line, which we found out was 1, and we're going to solve that. Okay, so I'm going to start off by subtracting 4 on both sides here. We'll do that first. I get negative 2x equals negative 3. I'm going to divide out the 2 on both sides. I get x equals negative 3 over negative 2, which is equal to 3/2 or 1.5 positive. All right, compare your answer to D, or compare your answer, that should say in D, to your estimated point in B. So notice in B, the x value of that coordinate on the graph right here was 1.5. And when we set f prime of x equal to the slope of the tangent line, we came up with x equals 1.5. So what happens here, what we can say here is the slope over the interval over 0 to 3, okay, that was 1, equals the slope of the tangent line at x equals 1.5. And as long as your graph is differentiable, then you're good to go. All right, let's take a look at some examples here. All right, so example number 2 says use the function f of x to answer the following. On the interval from 2 to 6, what is the average rate of change? An average rate of change just means calculate the slope. So here we go. We need f of 2 and f of 6. So f of 2 is equal to negative 2 squared plus 3 times 2 plus 10. And if you do your math on there, you're going to end up here with 18. If we do the same thing for 6, we would do f of 6 equals negative 6 squared plus 3 times 6 plus 10. And if you do that one, you're going to end up with negative 8. Now I can use those values to actually find the slope. So I'm going to do, let's see, I'm going to do negative 8, that's your y2 minus 18, y1, all over 6 minus 2. And let's see, that's going to be negative 26 over 4, which is equal to, we'll call it negative 13/2. I'm not going to do decimals on this one. I'm going to leave it as a fraction. So there's the slope from 2 to 6 on that particular parabola. Part B says on the interval 2 to 6, so notice this is an open interval, so somewhere between 2 and 6, when does the instantaneous rate of change, when they say instantaneous rate of change, they are saying when does f prime of x equal the average rate of change? And that is what we just found right there as negative 13/2. So the first thing we have to do then is we have to come up with the derivative, f prime. So I'm going to find f prime. F prime is going to be, let's see, we're taking the derivative, that's going to be negative 2x plus 3. And then we're going to set that equal to the average rate of change. So negative 2x plus 3 equals negative 13/2. All right, so most of us don't like dealing with fractions, so the first thing I'm going to do, I'm going to multiply both sides by 2 in order to clear out the fraction on the right side here. So when I multiply by 2 on the right, I just have negative 13, but I also need to multiply by 2 on the left, so that's negative 4x plus 6, which makes this maybe a little bit easier to solve. So I'm going to subtract 6 on both sides. We'll start off by doing that. I'm going to be left with negative 4x equals negative 19. Divide out the negative 4, you get x equals negative 19 over negative 4, which is just 19. Did I miss a negative in there somewhere? That's just 19 fourths. Okay. All right. So earlier in the semester, we talked about the intermediate value theorem. So we're going to just look at the difference between the mean value theorem and the intermediate value theorem. So the mean value theorem, which is what we just did, says that the derivative, the instantaneous rate of change, must equal the average rate of change somewhere inside of that interval. And that's the example that we just did, and the same on the front. The intermediate value theorem says on a given interval, you will have a y value at each of the endpoints of the interval. Okay, so maybe I have this graph that maybe looks something like this, and I've got a point over here and a point over here, and we'll say that, you know, maybe this is x equals 1 and x equals 10. Doesn't really matter. The intermediate value theorem says that every y value exists between these two y values at least once in the interval. So if this y value here is 2 and this one is, let's just say, I don't know, 20, okay? Just keeping things easy. That means that for every value in between 2 and 20, there exists another y value. So easiest way to show that is with a straight line. So I've got 3, 4, 5, I've got all the decimal values in there. You notice it says at least once. So maybe my graph does something like this, where now I have y values that repeat here and here. That's okay though. The intermediate value theorem says that there has to be a y value from 2 to 20, at least one in there. Okay? We can also look at this we're going to look at both of these with a chart here. So it says a hot air balloon is launched into the air with a human pilot. The twice differentiable function h, okay, that's h in the chart here. So they're telling us that h is twice differentiable, which means the first derivative exists and the second derivative exists. Models the balloon's height measured in feet at time t measured in minutes. The table below gives values of h of t of the balloon at selected times t. Part A says, for the interval from 5 to 15, okay, so in between here, 5 and 15, must there be a time t when the balloon is 50 feet in the air? Justify your answer. So in this interval, does the balloon hit 50 feet in the air? Well, if this function is differentiable, which it is, and it starts off at 40 feet and then it goes to 70 feet, it must have hit 50 feet somewhere in the air. So we would say yes. All right, so yes. Now, to justify this, we need to say, since h is differentiable, okay, differentiable. Because remember, if h is differentiable, then it's also continuous. All right, so since h is differentiable with h of 5 equal to 40, there's my low value, and h of 15 equal to 70, that's my high value, then there exists a c, so some value of c, in the interval from 5 to 15, 5 to 15, such that f of c would equal 50. Okay, and the reason we know that is because it's differentiable, so we're allowed to say that. And this is intermediate value theorem, IVT. The second part says, excuse me, for 20 to 30, okay, so now we're up in this interval here, 20 to 30. Must there be a time t when the balloon's velocity, okay, so velocity, remember, is the slope of position. This was basically a position function, h of t. when the balloon's velocity is 1.5 feet per minute? Well, in order to know that, I need to look at the endpoints of this interval, and I need to look at the slope over the interval. So I'm going to look at the slope. All right. So the slope in that interval, so we're going, use your x1, x1, x2, y1, y2. All right. So the slope in there is 80 minus 65 all over 30 minus 20. And if you do your math on that, that's 15. What do we got here? 15 over 10, which is equal to 1.5. So this is the average velocity. Okay, that's the average velocity over the interval. So because h is continuous, I'm going to say again, yes, since h is differentiable, and the average rate of change, over the interval, let's see, that was 20 to 30, is 1.5, then there exists some value of c in the interval, the open interval now, 20 to 30, such that f prime of c is equal to 1.5, and that is the mean value theorem. All right, have fun with those.